after our blowout. Yeah, you were. I don't know if y'all can tell. I feel like it's brighter and it looks better. Where it's kind of dull before, it's all like nice and clean and bright and white. And I like that. So we got a new board. Not a new board. We got a new light bulb. Let's see. Yeah, it's the exciting part of my Tuesday. I got a new light bulb in my room. Where am I? Oh, way too far down. Where are we at? Identifying minerals. We're going to identify some minerals. We're talking about how we do that, and we're going to look at the different properties of minerals that help us identify them. So let's see. I am recording. Good. Introduction to identifying minerals. Let's see. What are they talking about here? All right. Talking about an emery board. Corundum, spinel, magnetite, rutile. Okay, they're basically setting up everyday use of minerals in our everyday lives. And so they say, have you ever snagged your fingernail and it was driving you crazy? The easiest thing to do is reach for an emery board, which I don't know why. Like, if you've ever used these, they're really, really nice. I feel like 0% of guys use them. Am I wrong? Has anybody ever used the filing board? They work great and they're nice, but we don't use them. Like, if our nails messed up, we just chew it off and go about our business. Which, by the way, in coronavirus times is really gross. You should not be chewing on your nails unless you washed your hands thoroughly. But the emery boards, the little nail files work really well. And what they cover these in are just a bunch of really hard minerals. So corundum is like a 9, I think, on the hardness scale. So right underneath diamonds. Spinel's pretty hard. Magnetite's pretty hard. Rutile's pretty hard. You're talking 4 different minerals that are pretty high on the hardness list. So when I put powder on my little piece of cardboard and I scrape it up and down on my nails, now it's got some hardness and it can scrape away different layers of my fingernails, make them nice and smooth and ready to be painted up or whatever I'm trying to do with them. So, importance of minerals. Let's see what they got going on here. Oh, wait, hold on. I got my speaker on in the back. Let me change that. There we go. And let's see what they got to say here.
In which you are watching this video is electronic. Electronics are made from metals and other elements, which are found in minerals. The electricity that powers electronics is delivered through copper wire. Copper metal is found in various different minerals. The building you are in and the car you drive is made from steel, which is carbonized iron. A lot of iron comes from the mineral taconite, which is a type of iron ore. Modern technology is dependent upon minerals used in millions of manufactured products. Minerals impact every aspect of our lives. A mineral is an element or chemical compound formed as a result of geological processes. Let's learn more about minerals.
Okay, real quick. He makes a good point. Literally everything around us, unless it's like wood that grows from trees, we get it out of the ground and it's some sort of mineral or rock. We're not getting anything out of the air. We're not making anything out of air parts. We're not making anything out of parts of the water. We just drink water. Maybe you could call salt a product of water, but we're not processing a lot of materials out of water. We get a lot of that stuff from land. Every single bit of metal we ever get comes from minerals in the ground. Every bit of rock, every bit of plastic comes from oils that are minerals that we drill out of the ground. And so if we made something and it's not made of wood or like yarn or like cotton, we pulled it out of the ground and mined it from minerals. And so that's kind of important to remember. Most manufacturing has something to do with minerals.
Every metal and many substances used in manufacturing are extracted from naturally occurring forms called minerals. Minerals occur in rocks. Rocks that contain high concentrations of minerals are called ore. Ores contain enough valuable minerals to be mined for profit. For example, aluminum is widely used by industry from making soda cans to aircraft. Aluminum is made from a mineral called bauxite. Bauxite is the primary naturally occurring source of aluminum. Bauxite is mined from open pit mines. After mining, bauxite is processed to extract pure aluminum, which is further processed for use in manufacturing. Gypsum is a soft white or gray colored mineral that occurs mostly in sedimentary deposits. Gypsum is used in fertilizers and in many building products like sheetrock. Silicate minerals are widely used in many everyday products. Numerous different types of glass are based on silicate minerals. Glass is used for utensils, windows, and as an insulator. It's also used in optical transmission fibers for cable television, while the silicone chip is based on silicate minerals. Silica is also used as a filler in many cosmetics. Sand is the most common and readily available source of silica. It is mined from open-pit sand mines. A number of minerals are rare, and depending on their rarity, are considered to be precious or semi-precious. We're most familiar with their use in jewelry, but these minerals have many industrial applications. Gold and silver, for example, are both used extensively in jewelry and in industrial goods. Most gold and silver deposits lie deep underground. The mining of precious metals is complex and labor-intensive and requires large machines. Just about every aspect of our civilization depends on minerals in one way or another. Our use of minerals also comes at a cost. Mining and refining of minerals or their improper disposal can cause environmental problems. Minerals certainly impact every aspect of our lives and society.
All right, nice. That wasn't too bad. Okay. So let's keep going. We're not going to look at minerals and all about us. So let's get to the actual mineral identification part. So now we're on the Explore tab. How do we identify minerals? Basically, we're going to look at a handful of characteristics, and we're going to say, if I can identify something about that characteristic and kind of get a list going, that will help me figure out what mineral I have. And so we're going to go down the list of characteristics. Number one, which is kind of the most useful one that we use minerals for, is hardness. A lot of minerals have differing various hardnesses, from all the way to super hard things like diamonds or quartz that are really hard to scratch and break, to the really soft things like gypsum or talc that I can literally scratch with my fingernail, and they just like crumble into dust. And so hardness is all about how your molecules are connected. And the way that we test hardness is we scratch things. So note, if I take a diamond and like smash it with a hammer, the diamond is going to break. It's not going to survive that. What the hardness of a diamond is like if I take a knife and try to scratch the diamond, it's not going to scratch. That's what we do with hardness is we do a scratch test. And so you can either have something like a knife or a nail or a penny or your fingernail that you already know the hardness of, and you compare it by trying to scratch whatever mineral you have. If I can scratch it with my knife, then I know my knife is harder and the hardness of the mineral is softer than my knife. If I can't scratch it with my knife, then I know the mineral is harder than my knife, and that gives me some sort of range. Another thing you can do is try to scratch it with other minerals. So if I know quartz is a hardness of 7, I can take another mineral and try to scratch it with quartz, and that will tell me whether it's harder or softer than the quartz. So hardness is a big deal. We try to keep track of hardness, and that's a good way to identify minerals. The next thing is luster. Does anybody know what luster is?
Shininess?
Yes, it's the shininess. And so there's a lot of different ways you get into luster. And here's where geology gets a little fuzzy sometimes. Where other sciences, you got specific stuff that you're doing. With geology, sometimes we get a little loosey-goosey, you know? And luster is one of those, because the way we describe luster is not like an exact science. So we have a metallic luster. A metallic's pretty close to exact. Metals shine like other things don't shine. You never confuse a metal with like a piece of glass or like a diamond or anything, because metals have a very specific way that they shine. So metallic luster is pretty easy to see. You see a piece of metal and instantly recognize that's a piece of metal. Vitreous is going to be the type of shine that you see from a piece of glass or like a really hard plastic. That kind of clear shininess that metals don't have. So if it looks like glass, it's going to be a vitreous luster. Adamantine, I don't know if I've even seen adamantine. That's a weird like metal kind of shine to it. A pearly luster looks kind of like a pearl. If it's got that white like opalescent kind of color where you got a little bit of a rainbow effect, that's going to be a pearly luster. So like the inside of clamshells or like a pearl that comes out of a clam. Greasy luster, this is weird. Have you ever seen a rock that looks greasy? No. Probably not, because it's a really weird thing. But if I had a good sample, I could hand you this rock and you'd be like, it looks greasy. That's a greasy luster, and there's really not a great way to explain how it looks. It just kind of looks like it's coated in grease, which is weird. A waxy luster is kind of dull, like a wax candle, and then they have dull lusters. And there's a whole range of this. You can kind of almost add any word to different lusters. But there's a lot of different ways that things look and shine or don't shine. So luster is its shininess. Color's big. Note that color isn't great for identifying because there's a lot of minerals that can be a lot of different colors. For instance, quartz can be almost any color. At least keep your heads up. Hey, heads up. Yeah, we ain't sleeping. I can't make you pay attention, but you can at least keep your head up. So color, quartz can be pretty much any kind of color. Diamonds can be several different colors. Lots of minerals and gemstones can be different colors. So sometimes color helps. Sometimes color does not help. If you've ever seen sulfur, nothing really has a color like sulfur. Let me type up some sulfur here. Sulfur. So let's see. So see this yellow color sulfur? There's almost nothing that has a yellow color like that other than sulfur. That's a pretty good indicator of what mineral that is. Yeah. And then like olivine has this kind of olive green color. There's also not a lot of minerals that have that color, so that can be a pretty good identifier. But other than that, let me show you this minerals chart. Yeah, this is just some of the minerals that are there. There's literally like over 4,000 different minerals. And so just on this one chart, which literally doesn't even have 1,000 minerals, you can see all sorts of greens, all sorts of blues, all sorts of blacks and purples and browns and reds and yellows. So this is a good example that finding a mineral with a certain color doesn't really show you what that mineral is, because I can find another mineral that has a similar color, but it's a completely different mineral. Gold, yeah, nothing shines like gold. Gold is gold. Even the thing that's close to gold, which is fool's gold, it's pyrite. It's literally named fool's gold because you'd have to be a fool to think that it's gold. If you get gypped off by like taking a coin that's pyrite and not gold, you don't really even know what gold looks like. And so, yeah, I probably shouldn't have used the term gypped. Sorry. You just get used to things, and then you're like, oh, that's a bad word. I shouldn't use that. So, let's see. What am I doing now? Oh, what was I doing? Oh, I'm on this slide. My bad. So, we've got color here. Streak. Streak is basically a powder form of your color of your rock. And for most things, it's going to be the same. For some things, your streak is a different color. So what you're going to do, you take a porcelain plate, which they call a streak plate. It's like a little piece of tile. And you take your mineral and you scratch it along the plate, and it leaves like a powder behind. That powder can be a different color than your actual color of your mineral, and that can help you identify what kind of mineral it is. The next one is cleavage. And cleavage is actually a two-part kind of attribute here. So cleavage and fracture are like flip sides of the same coin. If I break a mineral and it breaks in a flat plane or like in a straight line with a flat side, that's cleavage. So if I have any flat sides on my mineral at all that are broken that way, it's going to have cleavage. If I don't have any flat sides, it's going to call fracture, and it just looks like a broken rock. With cleavage, and I wish they had pictures of these, you can have lots of different types of cleavage. And in fact, let me I don't know if I should do a Google search about this. Let me see if this works out. Back. I'm gonna make sure to type in mineral cleavage and hope this works out well. Yes, it did. Here we go. This is that's an okay example. I wish there was a bigger picture here. Yeah, there we go. No, that's crystal form. No, that'll work. Okay, my bad. Just going through some stuff. My bad. So this just kind of shows you some different types of mineral cleavage. So if it has just one direction of cleavage, it's going to break off into flat sheets, almost like little sheets of paper. If I have two directions of cleavage, I will have two flat sides, which if they're parallel, they only count as one. So the front and back of this would be one set of cleavage, and then these sides would be two sets. And you can see on this one, the top and bottom kind of look like roughly broken. That's because there's no cleavage on top or bottom. So that's why it's only two sides. If I get up to three sides of cleavage, actually I think that's four right there with the little diamonds. No, that's four. So this would be three sides of cleavage. They're just kind of tilted a little bit. But all sides, top, front, back, left, right, are all flat. And so all three directions, X, Y, and Z, all have flat sides. And then you can get into some real complicated stuff, like six-sided, four-sided, and even in three-sided ones, they can be 90 degrees or at an angle. So all of these break like this. This is an actual type of cleavage where your rock breaks and these flat planes and looks nice and neat. So that's cleavage. If it's fracture, it's just going to break. It's going to look like a broken piece of rock, just like every other rock that you've ever seen. It's just kind of jagged and non-flat. What else do we have? So they talk about the hardness scale a little bit. Note for the hardness scale, it's 1 to 10, and every whole number has a mineral that matches up with that. So the softest mineral, it's actually not the softest, but on the most hardness scale, talc is about a 1. Very, very soft. If I just rub it with my finger, it'll break apart into like powder, which is what we use, or we did use before modern manufacturing, for talcum powder, baby powder. That's the mineral talc. You can go to gypsum. They talked about gypsum in the video. We use it for fertilizing. Calcite, fluorite, apatite, orthoclase. Here at 6, you really start to get into the hard stuff. Feldspars and quartz are used for countertops and other building materials. Topaz, corundum, and diamonds are all gemstone quality minerals that we use for jewelry and rings and other stuff. And the reason is, if you pay a bunch of money for jewelry or for a ring, you don't want it to like smash apart the first time you accidentally smack it against a countertop or a wall or whatever you happen to be doing. You don't want these very expensive things to break. And so you don't choose a soft mineral to make your jewelry and your fancy stuff out of. You choose a really hard mineral so it lasts a really long time. Let's see. Other mineral characteristics. Crystal form is important. This is unlike the cleavage, which is how a rock breaks apart. Crystal form is how a rock grows into a certain shape and will always be that shape. So if you've ever seen quartz, I don't think I have anything out right now. If you've ever seen quartz with a nice like six-sided pencil-looking mineral, let's see, quartz crystal. Where are we at? I want to see it from like the top, kind of. That's not bad. So quartz forms this like six-sided, almost pencil-looking shape. This was not cut this way, and it didn't break this way. This is how the quartz crystal grew. And so it was always this shape from the point that it was like a tiny little crystal. And the more it grows, it's still going to keep this shape with 6 perfect sides. And at the top, those sides kind of taper in towards like a pencil end. Quartz grows this way all the time. And in fact, you see the natural quartz here with all these like clusters of crystals. If you just zoom in on one of those crystals, it will have 6 sides and kind of come to a point like this main crystal here. So they're all going to work the same because they grow that way. That's just how the molecules fit together. There's no other way they could fit together. What else do we have? Specific gravity is just a measure of density of the mineral. So how heavy is the mineral per its size? That can help me figure out some stuff. Will it dissolve in water or some other chemical? That can tell me what kind of minerals or what kind of elements are inside the mineral and tell me what mineral it is. Calcite will react to acid. If I drip acid on calcite, it will bubble and fizz. There's very few minerals that will do that. So if you ever go to a state park or some kind of outdoor nature kind of thing, if you see a group of people walking around with these little drop bottles dripping things on rocks, that's a geology class, and they're dripping acid on rocks to find out if it's calcite. Probably because they're lazy geology students and they just like to see things bubble and fizz. But we've all been there. Fluorescence and phosphorescence. Let's see. Let me see real quick. I wonder if I can get this going. I don't know. Give me a second. How much time do we have left in class?
5 minutes.
5 minutes. That ain't too bad.
All right.
Okay, we'll leave that going for just a second. So fluorescence is literally rocks that will grow or glow in black light. So you ever, what's the name of the store at the mall? What's the golf store at the mall? Hot Topic. You ever been? Y'all don't go to the mall? God, gotta go to the mall sometimes. Jeez, I know, but if you don't go to the malls, they'll all close down, and then we'll all be really sad. No, we won't. But if you ever go to the mall, you don't have to go to the mall. I don't know why I'm keying off on the mall. You ever seen like a black light poster where you got the black light and everything's glowing? Or you see a black light t-shirt where if you go in the black light, everything's glowing. There's rocks that will do that naturally. So that's fluorescence. And then you have phosphorescence, where some of them will glow even after the light is turned off. So they're like almost glow-in-the-dark rocks. This happens naturally. They're pretty rare, but it does happen naturally, and that's something that can be used industrially. Chatoyancy is where I have a bunch of fibers in my rock, and it kind of has a look if I move it around. This is called tiger's eye. And so as I take one of these and kind of move it back and forth, the stripes will kind of disappear or be highlighted, depending on how the light bounces off of it. That's chatoyancy. Double refraction. Calcite's really the only thing I think that does this. If I take a clear crystal and put it down on a piece of paper, it will take whatever's on the paper and double it. And so instead of one line of words, I see 2 lines of words. So it kind of splits it up. And then radioactivity, there are radioactive elements and minerals. And then magnetism, they can be magnetic, like magnetite, which is the key magnetic mineral. It's literally named after its magnetic properties, magnetite. Tenacity we don't use. That's more like an engineering thing. How well it'll stand up to like breaking apart. And then they talk a little bit about mineral identification. We're not going to do too much of it, but essentially you get a long list or kind of a little book full of mineral information, and you take all the stuff that you just learned about your mineral, what the hardness is, what the color is, does it have any of these special properties, does it have cleavage or fracture, what's the crystal shape, and you look them up in the book, and you try to identify your mineral and get the names from it. So you use a little bit of this information through everything to try to figure out what the name of the mineral is. And then if y'all will, real quick, everybody come around this way and file in here to this closet. And I want to show you these minerals in here. Come on in here. Just real quick. Come on in here. I know it's dark. Yeah, come on in here. And basically what we have here, these are my phosphorescent minerals. Some of them work better than others, but you can see they're kind of glowing in the dark here. This one's really popping off pretty well. You can see the nice orange glow in the dark. Turn the light on real quick. Right behind you on the wall here. Yeah. Somebody flip the light on. So you flip the light on, and they just look like normal rocks. There's no glowing. There's no color here. It's just like a black and white rock. But turn the light back off. Thank you. And you get the black light, and you get this nice orange. This one's got a nice green to it. That was not there before. Little orange, little green. There's some yellow stuff. You could get purple. They're pretty cool rocks. These are not the greatest. I've seen much better ones than this. And then I don't think, but we're going to check and see, are any of them phosphorescent, which means they'll glow after you take the light away. And I might not have had the light on them for too long. But let's see real quick if I can. Where's my switch? There it is. So we're just going to see, will they still glow? Nah, none of them are phosphorescent. But that's not too bad. And so in the right conditions, these rocks really put on a nice little show there. Wonderful. It's just a black and white rock. You can turn the light back on. So thank you. I appreciate y'all entertaining me and my rock collection. Yes. But that's the lecture for today. Tomorrow, God willing, if the creek don't rise, we will do an assignment on this. So, yes. Any questions? Any comments? Any concerns? Oh, gold's pretty soft. That's actually why you ever seen at the Olympics they bite the medals? It's because gold is soft. If you have a solid gold coin, that's how they used to check back in the day before we had technology. You bite it, and if it leaves teeth marks in it, then you know it's gold because gold's pretty soft. If it's like fool's gold or some other metal, or it's just gold plated, your teeth won't sink into it very much, and it won't leave a mark on it. Now, Olympic medals are no longer solid gold. So when you see them bite the metal, it's just something they do. They're not actually leaving teeth marks in it or checking it to see if it's gold. It's just like a tradition now. But yeah, gold is actually pretty soft. So gold, and that's why it's easily used for jewelry, because without melting it down, we can shape it into nice shapes and do intricate things with it. And that's why we kind of use it for that. So gold's pretty soft. Silver's pretty soft. But I think silver's a little harder than gold. And then you get into other metals like titanium and other stuff, and it gets a little bit harder. Let me see real quick. The hardest